As part of California's commitment to be a carbon-free energy state by 2050, every home in California will be switching to all-electric heating systems, otherwise known as heat pumps. So how does a heat pump work? We can begin to answer that by looking at how a standard home air conditioner works. A basic air conditioning system includes an indoor refrigerant coil with a blower, a return air grill filter and duct, a supply air duct and register, an indoor thermostat, an outdoor compressor, outdoor fan, and outdoor refrigerant coil, and an interconnecting refrigerant line set. There's an important key characteristic of a refrigerant. As the pressure increases within a contained vessel, the temperature of the refrigerant increases. Conversely, if the pressure decreases, the temperature of the refrigerant decreases. In a typical air conditioning cycle, the temperature increases, initiating a call for cooling from the thermostat. The indoor fan, the outdoor fan, and the compressor are all energized. The compressor reduces the pressure within the indoor coil, which reduces the temperature of the refrigerant and coil to around 45 degrees, and increases the pressure within the outdoor coil, which increases the temperature of the refrigerant and coil to around 120 degrees. The indoor blower passes warm air at, say, 80 degrees through the indoor coil. Since the indoor coil is 45 degrees, it picks up heat from the air, sending 60-degree air through the supply registers. This heat is transferred by the refrigerant to the outdoor unit, where the compressor increases the pressure and thus the temperature to 120 degrees. This means that the 95-degree outdoor air can withdraw the home's heat from the refrigerant, which returns in a liquid state back to the indoor coil. There, its pressure is once again reduced to a point where the temperature is 45 degrees. Here's what may be surprising. Your air conditioner is really a heat pump. It's pumping heat from within your home and exhausting it outdoors. If we reverse this cycle, we can pump heat from outside and use it to warm the home. We just need a refrigerant reversing valve in the outdoor unit. With this addition, our typical heating cycle goes like this. The temperature decreases, initiating a call for heating from the thermostat. The indoor fan, the outdoor fan, the reversing valve, and the compressor are energized. In the heating cycle, the compressor increases the pressure within the indoor coil, which increases the temperature of the refrigerant and coil to around 110 degrees, and decreases the pressure within the outdoor coil, which decreases the temperature of the refrigerant and coil to around 15 degrees. During this heating operation, the indoor blower passes cooler indoor air at, say, 65 degrees through the indoor coil. Since the indoor coil is now 110 degrees, it gives up its heat to the air, sending warm, 90-degree air through the supply registers. The refrigerant flows to the outdoor unit, and after the compressor reduces the pressure, and thus the temperature, to 15 degrees, it's able to extract heat from the 40-degree outdoor air. This is pressurized and pumped to the indoor coil at 110 degrees, where it passes its heat to the 65-degree indoor air, warming it up to 90 degrees. There's an additional cycle that our heat pump needs, called the defrost cycle, to deal with cold and wet outdoor weather conditions. This is required because the compressor reduces the outdoor coil temperature to around 15 degrees in order to be able to extract heat from the 40-degree or colder outdoor air. Because the coil is well below freezing, any moisture in the air will slowly build up as frost and ice on the coil. Over time, it will completely plug up the coil fins, restricting airflow and reducing the coil's ability to pick up heat. To deal with this, the heat pump controller puts the unit into defrost mode every 90 minutes or so to de-ice the coil by reversing the refrigerant flow. That is, returning to air conditioning mode, allowing it to extract heat from indoors and use it to heat up the outdoor coil to around 100 degrees, defrosting the coil in around 5 to 7 minutes. This creates a dilemma. Blowing 50-degree air into the home can be shocking. So to overcome this, we install an electric resistance heater inside the fan coil. During defrost, This heat strip turns on and re-tempers the air to a more tolerable 65 degrees so we don't cool the space further during the defrost cycle. Once the outdoor coil is fully de-iced, the defrost control reverses the refrigerant flow and reinitiates the heating cycle. Because heat pumps use clean, green electricity rather than products of combustion, they provide carbon-free comfort without the risk of carbon monoxide poisoning, flame rollouts, gas leaks, or soot. And because they move heat rather than make heat, they're about 3 times more efficient than either electric or gas heating. Another plus? They utilize reliable and familiar compressor and refrigerant systems, making service routine and commonly available.